So in today's lesson, we're going to be examining water and its role in equilibrium systems. And so what I've depicted here is what's referred to as the autoionization of water. So auto meaning self and ionization. So I have here a water molecule that's interacting with another water molecule, which happens all the time in solution, by the way. And so in previous lessons, we've identified that water is an amphiprotic molecule, meaning that it can both accept and donate a hydrogen ion or a proton. And so, if we designate one of these particles as a base, and one of these particles is water molecules is acting as an acid, then we know that our acid is going to act as acids do in the Bronsted-Lowry definition and donate a proton. And so in donating a proton, that one water molecule becomes a hydroxide, which we see over here on the product side. The other water molecule acts as a base because, of course, it's accepting a proton from the other water molecule. And when this water molecule on the leftmost side accepts that proton, it becomes a hydronium ion, which is what we see over here. So, knowing what we know about equilibrium, we can set up an equilibrium law for this, just as we have for many other chemical reactions. So I'm going to just write this generically as K is equal to the product of hydronium ions times the concentration of hydroxide ions. Since their coefficients are 1, the exponents in here are 1. But I'm going to go and I'm going to go over here and remind you that our water molecules are liquid. And so even though we might have the tendency to want to write out H2O, there are two of them squared, we actually don't want to do that. And so, very specifically, because we're talking about the autoionization of water, what we're left with is essentially just the ion product for water. And that has a special name. It's referred to not simply as K, but Kw, with that subscript indicating that it's referring to the autoionization of water. So, at 25 degrees Celsius, we know this through experimentation, but the Kw for water, which we know to be, let's just rewrite this up here. So Kw being equal to the hydronium ion concentration times the hydroxide ion concentration. If I substitute in what we know is true at 25 degrees Celsius for water, we know that its ion concentrations happen to be each 1.0 times 10 to the negative 7 moles per liter. We can easily substitute that into our ion product for water, 1.0 times 10 to the negative 7 times 1.0 times 10 to the negative 7, and that gives us a value for Kw that is a constant that is true at 25 degrees Celsius for solutions containing water, and that's 1.0 times 10 to the negative 14. Okay, so that's a value that I want you to kind of know and remember almost like as a constant. And so in the questions that we're about to do, and any questions moving forward, unless otherwise stated, we're going to assume we're talking about a reaction that's happening at 25 degrees Celsius. The value of Kw will increase as the temperature of the system is increased. And I want you to maybe take a minute to think about why that's true and how we can determine whether the autoionization of water is endothermic or exothermic. So pause the video and try to work that out on your own, and then I'm going to show you my own little way of thinking about this. So I'm going to write out that equation for the autoionization of water, H2O. I'm just going to write a 2 here. Those are liquid reacting to make hydronium ions and hydroxide ions. But I'm going to write that out twice. You'll see why in a second. So there we go. And I'm going to, picture a scenario where I'm looking at a reaction that is exothermic. So in other words, energy is going to appear as a product. And in the other case, I'm going to look at energy, being an endothermic reaction, and energy being a reactant. Okay, so if I were to look at the, and all of this, I'm going to remember that Kw is really just a product of the hydronium ion concentrations and our hydroxide ion concentrations. So essentially, any process that increases the concentration of one or both of my hydronium hydroxide concentrations is going to cause an increase in Kw. And so I'm going to be looking for which of these two situations are going to cause a shift in the reaction to the product side to make more of said ions. And so let's look at this. If Kw increases with temperature, let's see what the net effect is if I increase the temperature of an exothermic reaction. Well, I know that if I were to increase the temperature of this first reaction, we'll call this equation number 1, then that's going to cause a net shift towards the left. And that's not what I want. Because, increasing the temperature would cause my hydronium ion concentration and my hydroxide ion concentration to go down. However, if I were to increase the temperature of an endothermic reaction, then that would create an excess of energy, shifting my equilibrium to the product side and thereby increasing the concentration of my ions. So I can therefore say that since Kw increases with temperature, that the autoionization of water is endothermic. Now you can simply commit that to memory, but I personally like to be able to think about it so that it's just one less thing I have to remember. All right, so let's take a look at some basic criteria that I'm hoping you remember from grade 11 and even grade 10 science to some degree, which is that, first and foremost, a solution is considered neutral when the hydronium ion concentration is equal to the hydroxide ion concentration, because then those are able to neutralize each other effectively, leaving no excess of either hydronium or hydroxide. In an acidic solution, for a solution to be considered acidic, I would want to see my hydroxide ion concentration being less than my hydronium. In other words, there would have to be an excess of hydronium present in solution to make that particular solution acidic. And so the opposite obviously holds true for solutions that are alkaline or basic, where I would expect the hydroxide ion concentration to be greater than the hydronium ion concentration. So in the next slide, I want to quantify this a bit. I want to show you the type of question you might see in this section that you may have to use Kw and your understanding of relative hydroxide hydronium ion concentration. Let's take a look. So in this question, it reads, a sample of blood was found to have a hydronium ion concentration of 4.6 times 10 to the negative 8 moles per liter. And I want to say that blood pH should be around 7.3, but don't hold me to that. Somebody's going to Google it now, I'm sure. Out myself, and I saw that blood pH should be in the 7.35. Oops, let me actually write that out. 7.35 to 7.45 range, and that's normal blood pH, by the way. So find the molar concentration of hydroxide and decide whether the solution was acidic, basic, or neutral. Okay, so in this case, what I'm going to do is I am going to write out some givens. So first of all, I'm given that the hydronium ion concentration is 4.6 times 10 to the negative 8 moles per liter. And I also know that I am looking for the hydroxide ion concentration. And, based on my pH here, I'm going to expect that this is fairly neutral, but I'm going to also expect that my hydroxide ion concentration should be, a little bit higher than my hydronium, but probably not by much. And that's just assuming that this is a sample of blood from a person who's healthy, but who knows? And in fact, that might be exactly what's being tested to look for metabolic acidosis or alkalosis. So I'm going to use Kw in this case. And again, we're going to assume this reaction or this situation is happening at room temperature. And we're going to go ahead and say that our Kw is 1.0 times 10 to the negative 14. So Kw, I know, represents the auto-dissociation of water and can be written as such. And so I'm simply going to substitute in my known values, 1.0 times 10 to the negative 14 for Kw. My hydronium ion concentration, I know, is 4.6 times 10 to the negative 8 moles per liter, as given in this question. And my unknown concentration is, of course, my hydroxide ion concentration. So going about this and isolating my hydroxide ion concentration, I'm getting the value 2.2 times 10 to the negative 1, 2, 3, 4, 5, 6, 7 moles per liter. And I was right. So in this case, I can see that if my hydroxide ion concentration was to a power of negative 8, and my, sorry, that was my hydronium ion concentration, and my hydroxide ion concentration is to the power of negative 7, then my hydroxide ion concentration is greater than that of my hydronium, and therefore I can say that the blood sample in this case is alkaline or basic. It's a base. Okay, so that is it for this screencast. I hope you found that straightforward. In our unit plan, or week plan rather, there will be a practice question for you to try. And I would suggest you do that before moving on to the next screencast.